So I want to talk about the history and the geometry of the Kepler's law, and this is the Kepler's law of planetary motions. So when I say history of the Kepler's laws, it's the history of the discovery mostly, and well, also the background and a little bit about the consequences. So this happened at the dawn of the scientific revolution, which, as you surely know, changed the way humans live in a drastic way. All our current civilization is basically formed as a result of this process. And this was the late 16th, early beginning of the 17th century. And then I want to recall a little bit about what was known about planetary motions at the time, because people thought, observed the stars and the planets and thought about how they move for a very long time. And for many centuries, more than a millennium, the prevailing theory was the so-called Ptolemaic system. So Claudius Ptolemy, this was the kind of high point, a summary of the thinking of ancient Greeks about this, and he wrote this book, Almagest, in around in the 2nd century AD. And so this was a brilliant solution to a mathematical problem, and the problem was as follows. So Greeks thought that the world is governed, the motion of planets should be somehow based on the uniform circular motion. So they centered at Earth. So here is the Earth, and things just move this way. But then when they observed the stars, they observe the sky, it doesn't quite match the picture. It's kind of, at the very first approximation it does, but as the observations get better, it turns out that that's not how the sun and the planets move. Especially like with the sun, it's close to circular but not uniform, not quite uniform. With the planets, there is this so-called retrograde movement, so they kind of move and then they go back a little bit and then they continue. And so they developed a theory. And okay, we don't have the projector, so I'll just, the room is small, so I'll just show you. Maybe you can see a little bit. Okay, so it's coming. Anyway, okay, I'll talk about this and then.
What type of projector is needed?
Yeah. So it was quite involved kind of system. Where basically they say that, okay, so still they want to think about the things centered somewhere on Earth, or then they had to accept that maybe it's centered somewhere near Earth. And then there is a circular, well, that's why I remember the slides, because my circles are not very circular, but okay. So, and then there is something moving around the circle. But this something is sort of not something we see. this something is the center of another smaller circle, which in turn rotates. And the planet sits somewhere here. And then there is a further correction. So in fact, it's not exactly uniform, but they say that, so this is called, I think, different. And they say it's uniform if seen from some another imaginary point, equant. So it's basically the angular velocity if seen from this point is kind of constant. And then that's basically, and then this motion is uniform. And somehow they twitch the parameters so that it basically agrees with the observation. In fact, I think for some planets it's even more complicated, and you need yet another circle centered on this. So yeah, there's yet another imaginary point which moved as I just described, and then there was something moving around this. And I think it's a very interesting mathematical kind of story to understand why they were able to develop a system like that really worked. But of course, from the modern perspective, this is a very, I mean, this has nothing to do with nature, basically. It's you develop some mathematical scheme, but so, you know, in nature there are no they, I think, imagine the actual sphere that kind of exists there and to which the stars or planets are attached. But, I mean, this is a complete nonsense from a modern perspective. And yeah, so I had this nice picture which basically illustrated this, which you can maybe see a little bit here. But it's a nice picture that reproduces this same thing. Okay, so fine, and so the first step, and actually I looked up, and some people say that the beginning of the scientific revolution, of course, it's not well-defined beginning and end. But many people say that this is the publication by Copernicus of his book on revolution of heavenly spheres. And so Copernicus in around 1543, towards the end of his life, and so he published an influential book which was insisting on heliocentric system. But it's kind of an interesting point because he was insisting on this system, but he had no, in terms of describing then how the planets move, he had nothing better to offer than these old ideas about imaginary spheres rotating there. And then so Kepler was one of the people, and perhaps the most talented one, thinking about these questions a generation later. And so let me give his years of life. So Kepler 1571 to 1630. And so he wrote these long manuscripts where he, in particular, described the process of his discovery, among other things. And so on July 9, 1595, so Kepler was young guy, so he was 24 years old. And he had a position of a teacher of geometry and astronomy in, I think it's even a small city now, but Graz in Austria these days. I think now it's spelled Graz. Doesn't matter. So he was giving his class, and in the process he drew something like this. He drew a triangle, one of the things people draw in geometry classes. And then there was a circle around this triangle, and then there was a triangle around this circle, something like this. And then he had a flash of an insight. He had this sort of revelation. So he thought that, that actually this has something to do with how planets move around the sun. So the point is that at the time, there were 6 planets known. So now there are 8, and for a while there were 9, but then Pluto was, Pluto had the status of the planet for several decades, but no longer. But anyway, so, and then there are 5 Platonic solids. So these are, these are the regular polytopes, right? The regular polyhedra. So just to remind you how they look like, here is a standard picture. So there is a tetrahedron, and then a cube, and then there is icosahedron, dodecahedron, and what did I forget? Octahedron. And so then what his idea was is that the planets should be arranged around the sun in the following way. That there is a, just like in this picture, that, like the outermost planet, Saturn, it moves on a big sphere. Oh, okay, great. It moves on a big sphere. Thanks. And then inside we have something inscribed, one of these Platonic bodies. And then there is a next sphere inscribed in that thing, etc. So, of course, from modern perspective, it's complete nonsense, and it's even, has much less basis than the old Ptolemean system. But he was sure that that's how it works. And he, was very excited about it. He wrote a book, which was called Mysterium Mysterium, I think actually appropriately from the modern perspective, Cosmographicum. It was all in Latin. And so here is an illustration from that book, I guess. So you see that there is this outer sphere, and then inside you have a cube, and inside there is a smaller sphere, and inside there is an tetrahedron, etc. And the idea is that Platonic bodies kind of govern this universe in some sense. It was actually very old. Just for the context, I want to say that it's already in Plato. So in his dialogue, Timaeus, so Plato actually talks about how elements are made of regular Platonic bodies, and so they say that he says that Earth corresponds to cube, and the air to octahedron, and water to icosahedron, and fire to tetrahedron, which is again doesn't have much to do with reality from our modern perspective. And actually, in this Plato's text, Timaeus is 360 BC, so it's 2 millennia before Kepler. And he remarks there that the god used the octahedron, so there are four things here. Sorry, not octahedron, but the last one is the dodecahedron. So the god used it for arranging the constellations on the whole heaven. So in a way, there is this idea that this should be used in celestial mechanics, and maybe there are other precursors. But in any case, so this is the idea on which Kepler converged. And so now the interesting thing is that, if he ended there, then we probably wouldn't be remembering him. But he was a mathematical genius, and he actually went to great lengths to work out, the details, to get the best observations that were available at the time, which also wasn't easy for him. Practically, he wasn't a rich man, but he did it, and then to kind of work on the mathematics of it and to, see why and how it all works out. And in the process of doing so, he discovered the correct laws, but somehow he didn't completely part with this original idea which was driving him until the end. So even his kind of final book that he wrote not long before his death, there are many insights. In particular, there are correct laws which we will discuss now. But he's still playing with this idea somehow. And so there's a beautiful book about this, and in general about development of the humanities understanding of the celestial mechanics, and it's by sleepwalkers. By Arthur Koestler, which I highly recommend. And he, his point, he presents all this history, and he emphasizes how at various turns people were driven by kind of wrong rational ideas, but somehow intuition was guiding them towards the right solution. So, just the title already tells us also they were like sleepwalkers, which were kind of going to reaching their destination. I want to offer a slightly different perspective, at least on this Kepler story, is that, you should be true to your ideas and try to, do your best to develop them. And, maybe they will turn out to be wrong eventually, but, that's the way to realize your potential and reach whatever results you can reach. Okay, so that's basically what and so just maybe a last remark on this history part is that just about the significance of this, significance, it's hard to overestimate it because the actual great discovery of, the great success of this new scientific methods was Newton's laws, but Newton, Newton's Principia. So for Newton, so this was 1687. And yeah, I should say that Kepler's, so I mentioned this book where he explained his wrong ideas, but the book which already contained the right ideas was published soon after, I think 10 years or so 1609. So you see that things, started developing very rapidly compared to, millennia of people staying with the same ideas. But so yeah, I just want to mention that for Newton, the very important part of this book is working with Kepler's laws and somehow arguing that Newton's laws, they kind of imply Kepler's laws. You can derive this from this. And this was a very important confirmation for these laws that Newton discovered that, we now learn in high school physics or middle school physics. This discovery of Kepler really opened the way to development of, not just theoretical understanding of not just celestial mechanics, but the mechanics in general, the world, physical world in general. Okay, so what are these laws? So now let's talk about this. Okay, so there are three laws, and so planets move on the orbits, and each of these orbits is an ellipse. So this is the idea that was very alien to ancient Greeks. So with one focus, with one of the two foci at the sun. So I will recall what this means in a few minutes. But two. Oh. Yeah, so I'll unlock it. And it's actually maybe a very appropriate time for the next picture. So yeah, this is a schematic picture. So this is the sun at the center, and the planet moves on an orbit like this. So and then so we'll maybe just introduce the notation, and so it will be convenient as we usually do. So there's a sun at the origin, then we have a planet, and then at time t we have this position of the planet, which is described by the, let's just write r of t, so for this vector connecting the sun to the planet. So we can just describe the position by this vector. And so yeah, so we also want to know how they move to describe the speed. And so it moves so that the vector, so r of t, sweeps equal areas in equal times. So again, so it will necessarily be faster when it's closer to the sun and slower when it's there. But so just if I draw this sector so that the areas is the same, then they will be traversed in equal times. And 3 is that the period of the planet orbiting its, going on its orbit is proportional to the major semi-axis, so to diameter, to g, to the power 3/2, so i.e. square root of g cubed, where actually, yeah, I won't need it for a while. But where d is this what's called major axis, or just the diameter. So if you think about it, it's basically describes the motion completely. And so what I want to do in the remaining time is, or at least most of it in the remaining time, is that we have, of course, know the Newton's law, gravity, that we have a force. So we have a sun, and of course, this is all works if we don't take into account various other things like gravitational force between the planets. But so within this framework of Newton's mechanics, and this is what people call two-body problem, so we have the sun S, and so we have the planet P, and we have a force acting on the planet towards the sun. And so the force F is proportional to 1 over the distance squared. And then, of course, the and acceleration, so if we know the mass of the planet, then acceleration is determined by this force and by the mass, and so the acceleration is also proportional to 1 over the distance squared. And so what I want to explain is how to derive this Kepler's laws from this Newton's laws. Okay, so the first, so that's basically the problem that Newton solved in his time. And, I'm not sure if it will be exactly the same solution. But. Okay, so let me start with the second law. Second law is actually the one which is the most transparent from modern perspective. This is really, but it was perhaps the most important exactly for this reason, because it's somehow basic and fundamental for the history of science, that somehow Newton explained this. And I must say that, yeah, this is, as you'll see, it's, clear from the first principles based on Newton mechanics, but this gave a lot of trouble for Kepler and his contemporaries, so they were somehow, maybe they were not alien to the idea that, it should be, the planet should be pulled towards the sun, but somehow, why does it move uniformly in the other direction? But yeah, this is basically how Newton's law works. So I will give an, not. So this is basically what's now called conservation of angular momentum. And so I will just to simplify the formula, so I assume that acceleration is equal to 1 over the distance squared. So I'll just set, various units to 1. Or choose various units so that this one. And so, okay, so let's look at this. Actually, yeah, don't need it for a while, so we can wait here. So here's the planet. So here's the sun. So here's the planet. And we'll look so in small time. T. So here, so suppose P was here at time t0, and then I let my clock run for a little while, and so I want to understand the area which was swept by this radius vector in that small time. So the area swept. Okay, I will write this sort of not quite rigorous argument, talking about what happens in small times and things being approximate. And once you learn derivatives, you'll know how to make it into a rigorous argument. But for getting a general idea, it should be fine. So first of all, in small time t, the area swept by this R of t is the area of this triangle. Of course, it's not exactly that, because it was moving in some funny orbit, but yeah, the area of this thing is really small compared. I mean, it's small compared to t. So is the area, so this is R of t0, and this is R of t 0 plus t. Is approximately the area of the shaded triangle. Okay, and now, yeah, so maybe that's right, p prime. And so we have this vector. So the vector p prime, it's approximately, again, equal to t times the velocity, right? T times v of t0. So this is the velocity vector. I mean, that's what velocity is, right? In first approximation, in linear approximation, if the motion was uniform, then after time t, we would have moved by that amount, right? Okay, sorry, yeah, this should be boring for the experts. So now, so we basically can think of this triangle as spanned by these two vectors, SP and this one. So we have the area of the triangle spanned by, so I go remember this word. So this is R of t0 and V of t0. So by this, I mean the area of the corresponding triangle. So here there is this little bit of geometry of vectors, which is useful. And so this is the area of two vectors, VW. In fact, there is a little trick here that you want to talk about the signed area. And so somehow if the second vector looks, say, up, then you count it with plus sign, otherwise with minus sign. And so I'll just write this here, is additive. I mean, maybe adds. Yeah, I'll just write additive. So by which I mean that area of VW1 plus W2 is A of VW1 plus A of VW2. And same if I fix W and add two versions for V. And this is actually clear because from elementary geometry, because if I fix V, then what is this area? I just have to, if you remember the formula for the area of a triangle, it's the product of the base by the height, and the height, it's a projection to the orthogonal, and it's clearly additive. Okay, that's nice. And now, how am I going to use it? Because now I'm going to use my law. And by the way, here I will only use the fact that the force pulls the planet towards the sun. I will not use the exact nature of the Newton's law, that is proportional to 1 over r square. And basically now we argue that, so check, now we check that this area of, again, R of t, well, V of R of S, V of S is constant, independent of the time S. And for this, I again look at this infinitesimal change of this. And so compare S equal to T0 and S equal to T0 plus T. Well, and now we do our final calculation. So we say that R of T plus T of T0 plus T is approximately R of T0 plus TV of t0 and v of t0 plus t. Well, now finally the acceleration comes in. And so what is acceleration? It's the velocity of change of the velocity vector. So this is approximately v of t0 plus t times what? Times the acceleration vector, which pulls towards the sun. So you can symbolically write it actually as minus r of t0 divided by r of t0 cube. It's just because, that's the formula for this vector, right? Because r of t0 looks this way and has this length, but now we want something which looks the other way and hence has the length 1 over the length of that squared, but so you have to divide by cube to, sorry, I don't say by cube. You divide by cube to get the right length. But okay, so, and even so, this factor is not important for now. It will be important later. But for now, we only say that, so let's just expand this using the additivity, but the thing is that, so area of r of t0 plus t, v of t0 plus t. Okay, so we just open the bracket. So it's a of r of t0, v of t0. And then the funny thing is that somehow we get this t a of v of t0 and the second. And so we get again v of t0, right? But so that means that we have to compute the area of the kind of degenerate triangle, right, formed by two collinear vectors. So this is 0. And then we'll get another term, which will again be of the same nature. So it will be again t of a of now r of t0. And then there will be minus r of t0. And then, okay, there will be some factors, but this is not important for now. Again, they're collinear, and so this is again 0. And then there will be something which is not 0, but this has this factor t squared, and so this is small if t is small. If t is small, and so it's too small if t is small, smaller than t. So we actually only have to keep track of the linear terms. So this is the argument which, this, I must say, is pretty standard, and again, can be made in a completely rigorous argument using derivatives. Okay, so now let me move to something more interesting. And okay, so any questions here? Okay, this is, this is standard but important, and a similar, so this was conservation of angular momentum, but there is also conservation of energy, which I will not, just to save time, I will not derive it, but it can be derived in a pretty similar fashion. So conservation of energy. So this is E, which is, well, as you know, it's sum over potential energy, but which is mv of t squared, but in my, I set all the constants equal to 1. So it's v of t squared over 2 minus 1 over the distance from the sun. So this is the kinetic energy, and this is the potential energy. And so this is also constant. Okay. And so now I want to do a little calculation. And now finally I will need to say something about the orbit. And so I will need to talk about the ellipse. So what is an ellipse? So ellipse. So you take 2 points and you fix some r, and you look at the set of all points such that the sum of distances, So this is F1, this is F2, and this is point P. And so ellipses is locus of the points where the sum of these two distances is fixed. Well, it's fixed and it's actually equal to, if you apply it to one of these 2 points, you see that it's equal to D, which is, well, this is D. And maybe another thing that, this, of course. Another thing we may want to know about the ellipse is that if it can be obtained from just a circle is a degenerate example of an ellipse, of course, when F1 is equal to F2. By the way, for the planets, the ellipses are not, I mean, they're ellipses, but they're kind of not very different from the circle. That's maybe why the methods of the Greeks kind of worked. But so, but if you take any ellipse, and so you can draw a circle with the same diameter, and you can obtain the ellipse by you can obtain the circle from the ellipse by dilating one of the coordinates. I mean, dilating it in this direction. So just applying the transformation, which x, y goes to x lambda y. Okay, so there are other beautiful things to say about this geometrical figure. I mean, it's one of the conic sections. But let's not go into this. So what I want to explain now is so okay, I don't know if I have time for everything. So maybe I'll go into yeah. So this is next section is you can discuss the third law. Okay, let me just say briefly how it works. So I want like the next law of complication is the third law from the first law. I'll just say what kind of calculations you need to do to argue this. So here how it works. So first, suppose we already know they run on ellipses, but how to see that the period is proportional to this distance. So the first thing to say here is that compute that the energy of the orbit only depends on d. So how to see this? So you compute, you look at these two, at those 2 points, right? And then you just get two linear equations in 2 variables. So we have the velocity. So on the one hand, so we have the velocity here. These are called basic, by the way, aphelion and perihelion in the celestial mechanics. So this is the Helios is the sun, and this is where it's closest to the sun, farthest from the sun. And so we have this, say it moves this way, so we have this VA, and we have this VP. And so if this is the sun, and if this distance is A and this distance is P, then we know that on the one hand, because of this fact that so I'm also using the law that I already established about this second law about the areas. And because of this areas law, we know that VA is inversely proportional to to a squared times a squared is equal to Vp times p squared. Plus we have the conservation of energy, but also Va squared over 2 minus 1 over A is equal to Vp square over 2 minus 1 over P. And okay, so from this you just you can do it yourself. So you can just derive the formula that E is basically maybe 1 over D. And another, you can do a similar calculation, which I would just want to say now, that the product will be maybe important later. The product VA times VP also only depends on E. It's equal to something like E squared. You can also just substitute these formulas and you get an exercise. Okay, so now how do we, so this will not play a role for now, but so how do we conclude? Now we look at this point. We look at, so this was supposed to be the, nice ellipse, and so this major x is supposed to be horizontal. But now let's look at what happens at this top point. Okay, so things simplify, but so on the one hand, because of this rule that you can obtain this thing from by dilating one of the coordinates, we know that the area of the ellipse is is proportional to this height. But on the other hand, you can easily, from the conservation of law, or conservation of energy, you can easily compute this velocity. And you see that this area velocity also proportional. And so you get the okay, so and from this you see that the period only depends, so the period only depends on the major axis, on D. So from this period, it depends on D. And it's easy to see how it works under scaling, and so you get the third law. Okay, so I'm basically out of time, but I wanted briefly to talk about the most interesting thing about the first law. So the first law, you can derive it from the so-called hodographic property. So it turns out, so this beautiful geometric fact, that the velocity vectors, they sweep a circle, which is, so this is shown here on the picture. So again, this is just the set of velocity vectors just drawn from an origin. So yeah, this is also kind of exercise. So you can think about you reparameterize the motion. Yeah, okay, maybe I'm not. So it's not an easy exercise, but it can be done. So just this to emphasize that. So here is how the actual planet moves, and here is what the velocity vector does. And from this, you can, knowing the this hodographic property, you can derive the first law in the following way: that you draw an auxiliary circle here and put a point somewhere, and then there is this following geometric construction that if you take a vector connecting it, sun to the center to origin of the coordinate system to a point on the circle, and then you draw a perpendicular and a middle orthogonal. Then, and you do it for all points, so I'll just do it for one point. Then they will all be tangent to a certain ellipse. And moreover, if you make the length, so if you draw a vector this way, whose length is inversely proportional to this, and make it a velocity, kind of, you move on this ellipse and make this the velocity vector, then the equal areas law will hold. So this is kind of, basically allows you to prove the first law. And let me end. So there was non-Euclidean geometry in the title, and just add one sentence. So you can ask, so this is a stereographic projection. And so you can ask, so which, so fixed energy. So which circles are swept by velocity vectors for various orbits with this energy? And the answer, there is a very beautiful answer, which is based on this remark here that I said the product is, has the form in terms of energy, which its role wasn't clear then. So it turns out that you can take a three-dimensional sphere, imagine a three-dimensional sphere, and consider the stereographic projection from that sphere to our 3 space. And then you can take various big circles on these 3 spheres, this kind of various sections with centers at the center of the sphere, and take their projections. And this is the answer. So projections of big spheres. What does it have to do with non-Euclidean geometries? Non-Euclidean geometry, this sphere is a model for non-Euclidean geometry where there are no parallels. So it's so-called positive curvature geometry. These are kind of analogs. Big circles play the role of lines in this world. And so there is a deeper connection, which I don't have time to explore, but so between this kind of spherical geometry and orbits of planets. And well, there are also comments about which I didn't talk. So there are things which run on hyperbolas, and these are related to hyperbolic geometry. So this will be a topic for another talk. But basically, I just want to say that in a sense, Kepler's intuition was right, and this problem in much of nature is built on symmetry, but not, of course, in that way. But the symmetry is somehow governs the laws of nature. OK, thanks.